I'm going to go over a few of these proofs without words. This first one that you can see, we have one dot, one gray dot, two gray dots, one gray dot, two gray dots, three gray dots, four gray dots, five gray dots, six gray dots. So it's like 1 plus 2 plus 3 plus 4 plus 5 plus 6. And then flipped over, we have, coming from the bottom, one black dot, two black dots, 3, 4, 5, 6. Together, they fit together to make a rectangle of points, of circles. And the dimensions of that rectangle are n, which is 6 in this case, and the base is n plus 1. So all the dots are n times n plus 1, but half of them are gray, half are black, so the gray ones are n times n plus 1 over 2. The second one is very cool. We have one dot, and it's a square, because it's a 1 by 1 square. Then when we add on the next odd number, these next 3, now we have a square, a 2 by 2 square. And when I add on the next odd number, which is 5, I get a 3 by 3 square. And this pattern seems like it will continue. So we'll always have a perfect square. Now, to see why the next odd number is going to make one of these L-shaped things that is definitely going to create the new square, one way to look at it is, here we just added 5. Now what is 7? Well, 7 is 3 plus 3 plus 1. So here's like 3, and here's 3 more, and then the 1 makes the 7. Another way to think of it is, over here I have the same 5 as I had before with the gray layer, and I'm just adding on 2 more to make the next layer. Either way, it seems clear that anytime I add the next odd number, it's going to fill in one more sort of L-shaped thing, creating one more square, and it means that the sum of the odd consecutive odds always adds up to a perfect square, and it's the square of the number of odd numbers. In this one over here, we have these pyramids here. Each one of them is 1 squared plus 2 squared. You can see this is 1 squared. Then you have the second layer. Let's look at this pyramid. 1 squared, 2 squared is 4. There's 4 little blocks there. And then it keeps getting bigger, 3 squared, 4 squared. So each of these, so what we have is 3 times 1 squared plus 2 squared. It's 3 of them. And according to this picture, I could assemble the 3 things together to make a weird shaped thing that actually is not like a smooth rectangle or rectangular prism box type thing. So if you slice off, in this picture they're slicing off half of that top layer, and then they're moving this black piece to sort of fill in the puzzle. Well, what happens? You can see from the bottom here that this layer is n plus 1, because I have the n and then the extra 1, so there's the n plus 1. And this layer here, which is kind of just the base of this guy, or over here, is just n, so there's the n there. And when we assemble these things together, this little square ends up on there, so that the whole thing is actually n plus 1, and this is still n plus 1. But then when I slice this half off and move it over here, it ends up becoming n plus a half. So we get this formula, 1 squared plus 2 squared up to n squared. 3 of them, 3 of these 1 squared plus 2 squared up to n squared would be equal to this box, which is n times n plus 1 times n plus 1 half. But if you divide both sides, or multiply both sides by a third, you get this. This is going to be equivalent to the famous formula where the sum is actually equal to n times n plus 1 times 2n plus 1 over 6. That's the more traditional formula for that, but if you change that 6 into 2 times 3, and then you cancel this 2 out with this 2 and this 1, you end up with this equivalent version of it. This one's pretty interesting. What I have here on the left-hand side, I have 1 squared, this is 2 squared, this is 3 squared, 4 squared, 5 squared. And on the left, I have another 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Now in the middle, remember from before, this is 1 plus 3, this is 1 plus 3 plus 5, this is 1 plus 3 plus 5 plus 7, this is 1 plus 3 plus 5 plus 7 plus 9. Ways of writing the perfect squares is the sum of consecutive odds. So notice how there are 5 1s, and I could put those 5 1s here, yet there are only 4 3s, which I could line up here, 1, 2, 3, 4 3s, and there are 3 5s, which I could put like that, and there are 2 7s that I can put like that, and 1 9. So what I have here is 3 of those 1 squared plus 2 squares up to n squares. It becomes a big rectangle. The height of the rectangle is 1 plus 2 plus 3 up to n. You can see that. That's the heights of these little squares. 1 by 1, 2 by 2, 3 by 3. The bottom comes from this last thing. That last thing is 9, which is actually 2 times 5 minus 1. In general, this last thing is going to be 2n minus 1. But then we have this extra 2 here. So when I add 2, it becomes 2n plus 1. And it becomes this formula, 2n plus 1 times 1 plus 2 plus 3 up to n. But of course, we have a formula for 1 plus 2 plus 3 up to n, which is n times n plus 1 over 2. And then if I divide both sides by 3, this becomes a 6, which is the famous formula. This last one was a little bit better in color. What I see over here is 3 squared, 3 squared, 3 squared, and 3 times 3 squared is 3 cubed. And over here, it's 5 squared, 5 squared, 5 squared, 5 squared, 5 squared. So 5 times 5 squared is 5 cubed. And this little guy here is 1 cubed. Now, it's not so easy to see because of the way this is, the way this thing lacks color. I think it looks something like that. What basically happens is that you have 1, 2, 3, 4 squares, and then these two pieces together become a 4 squared, so you end up with 4 times 4 squared. And over here we could see it a little better. This is 2 squared, and this is half a 2 squared, and another half of a 2 squared, becoming 2 times 2 squared is 2 cubed. So in other words, this sort of configuration becomes a big square, which is on one hand 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. But on the other hand, if you look at the height of it, it's 1 plus 2 plus 3 plus 4 plus 5, and it's a square, so we get this. All the squares together equal that, but the big square has dimensions 1 plus 2 plus 3 up to n squared. And that, since we have a formula for 1 plus 2 plus 3 up to n, we get n times n plus 1 over 2, the whole thing squared.